All right, so we just finished up chapter 5, okay, which pretty much ends the first big part of this class, which was all algebra. Okay, studying different functions, how to draw them, how to solve equations. Now we're going to look at how to solve equations, how to draw things again, but now we're going to start looking at trig functions. Okay, so we're going to start trigonometry. Okay, so usually first thing I do is just look at that word and break it down and see if we can figure out what it means. So is there any part of that word that somebody recognizes, or they've seen that part of the word in another word somewhere else? Yep.
Metry.
Metry, yep.
It's like the study.
The study of is ology.
Oh.
Like biology, psychology, sociology, theology. That's study of. But metry, anyone know what that means? It almost looks like kind of another word, metric. Think about what the metric system is used for doing. Anybody know?
Measurement.
Measurement. So this is measurement. And how about anything else there? Someone recognize? Yeah? Try, what does that mean? 3. And I'm even going to extend it a little bit more to trigon. Gon means sided, right? So if you think of like octagon, hexagon, pentagon, well, those are all names of shapes with the prefix in front telling you how many sides. Well, this is the name of a 3-sided shape. We normally don't call it a trigon. We normally call it a triangle. But every 2D shape has a name ending in gon. Does anyone know the 4-sided shape that ends in gon? A lot of people know the word quadrilateral, but that's not gon. You need a prefix. Yep.
Tetragon?
Yep, tetragon. And if you've played Tetris, all the shapes in Tetris have 4 blocks, and that's where tetra comes from. If the blocks had 3 shapes...
Tetra comes from Tetris?
Tetris is named after tetra. Yeah, if I said it the other way, yeah, I messed up. So tetra, 4-sided, tri, 3. Right. So basically a lot of what we do in trigonometry is measuring 3-sided shapes. Finding how long sides are, how big angles are. For example, very typical kind of problem. You've got a building here. You're standing here. You are 100 feet away from the building, and you have a device that, like a transit, that lets you point a laser at the top of the building and get the exact angle. Maybe that's a 40-degree angle to the top of the building. What you basically just did is make a triangle, like this. That's a 90, that's a 40, and your length of the bottom of that triangle is 100 feet. So now we could figure out how tall the building is, which is basically finding the height of that triangle. Okay? So there's a sample problem we could do in right triangle trig. Here's another problem. This is going to represent land, water. Let's say we have 2 Coast Guard stations on the land. And the Coast Guard stations are maybe 1,000 feet apart. Or they could be lifeguard station, whatever you want. The two stations are 1,000 feet apart. There's a boat out here. It's nighttime and it's cloudy, so the boat can't see any stars, can't see any landmarks, and their GPS isn't working, but they have a light on the boat, and they want to know where they are. Okay? And their radio works. So each one of these Coast Guard stations can see the light on top of that boat. This station sees the light coming from that direction. Okay? They don't know how far away, but they can say, you know what, I see it coming from that way. Well, the other station can do the same thing. They don't know how far away the light is, but they can say, I see the light coming from that direction. If 2 different people can see the same thing, and the 2 people are in different spots, then they can figure out exactly what they're looking at. They have to work together to figure it out. That's called triangulating someone's position. You can figure out exactly where they are if two people can see them from different spots. So what we've done is we just made a triangle. What's a little harder about this problem is there's no right angle in it. So if you're familiar with like Pythagorean theorem or SOHCAHTOA, where you use opposite, adjacent, hypotenuse, you can't do any of that here. But you can still figure out exactly where that boat is with this information. You'd have to know the angle too. So maybe each Coast Guard station has a compass, and they say, all right, the light's coming from northeast, and they give you the compass direction. Well, the compass direction would be an angle. Okay, so we'd have a couple angles in there, and we could figure it out. Right, so that's some really practical stuff that we can do with trig. Figure out distances, lengths, angles, stuff like that. Other stuff we're going to do in trig is more abstract, it's more theoretical. Looking at formulas and trying to simplify them. Okay. Applications for that kind of stuff is more in calculus. It's much, much higher level application than something like this. Okay. But we'll do a lot of stuff with triangles in trig. So, one thing we are going to do a lot with is angles. And we're going to talk today about how we measure them. So I'll define what an angle is, how we measure it, the units we use, stuff like that. All right, so we're going to start looking at trigonometry. So, an angle is basically, it's made up of two rays, and each ray has a common starting point. Does anybody know what you call this point? Like here's a ray, there's a ray. What do you call that point? Yep.
Vertex.
It's called the vertex. Yep. So you take two rays, you put them together with a common vertex, and there you go. You just made an angle. Now, in that angle, the angle has two rays. One side is called the initial, the other side is called the terminal. And how do you know which side is which? Well, let's draw an angle like that. If you rotate counterclockwise between the rays, okay, the short way, where you end up is the terminal side. So start at one of the rays, stay between them, rotate counterclockwise. Where you end up is the terminal. So that's the terminal side of the angle. That's the initial. So it's a counterclockwise rotation between the two rays. So it just gives us a way to talk about each side of the angle. If I say, look at the initial side or look at the terminal side, now you have an idea of which one I want you to look at. Okay, here's another picture with the initial side on the bottom and the terminal side going up into the right. Now, technically, when you look at this picture, we have two angles. You've got the angle inside. You also have this angle outside. Most of the time, when we're talking about an angle, it's the one that's between the rays, not the one on the outside. Now, first thing I said to you is that an angle is made up of two rays. How many angles in that picture?
Yeah. 6. If you're counting the outside ones.
Just the inside ones.
3.
3. How many rays are in that picture that I just drew?
3. Oh, none.
None. There are no rays. So, when you draw an angle by itself, we generally draw rays. When you draw an angle inside of a polygon, we draw line segments. Okay? So, even though this is not the point where two rays meet, that's where two line segments meet, that's still considered an angle right there. That still is an angle. Any question on that? Okay. So, when we don't know an angle in trig, we're going to give it a variable name. Well, in algebra, what letter is used as a variable a lot? Yeah, use x. Y is also used a lot. Well, in trig, we don't use x and y when we're talking about an angle. We use Greek letters. These are 5 different Greek letters that we'll use throughout trig. Not all of them today. But does anybody know the name of this first Greek letter? First Greek letter in their alphabet.
Alpha.
Alpha. Yep, it's the Greek letter alpha. How about the second one? Does anyone know that one? Yeah. Yep, that is beta. It's kind of like a B, but it's a little bit longer on the side. How about the third one? Anyone know that one?
Romeo?
What did you say?
Romeo? That's the R, right?
That's I'm not sure exactly what Greek letter that would correspond to because I don't think Greek has the letter C, even though I think that is the third letter in their alphabet, but I'd have to double check that. So yeah, it's not an R though. It doesn't correspond to an R. What is it? No? Anyone else have a guess what it is?
Sigma.
It's not sigma, but that is a Greek letter. I don't see that one used for angles too much. That one's gamma. That's gamma.
Oh, that was my next guess.
This one we use a lot. This one is kind of like the X in trig. Yeah?
Omega.
Actually, the last one is omega. That looks like the W kind of, but the curved and little loop on itself. Yeah.
Theta.
That's theta. Theta. And the last one's omega. Now, if you look at omega and you say, well, I thought this was omega. It is.
It's capital Omega.
It's capital omega. It's like saying, well, I thought this is B. Well, so is that. Just capital versus lowercase. All right,
Yeah,
so
I don't know the lowercase ones.
in Greek, we generally don't use the capital letters. We just stick with these lowercase ones. But just like in English, sometimes a capital and a lowercase can look the same. Like the letter C in English. They kind of look the same unless you have other letters around it to see the size. But those are the ones we use. All right. So Greek letters used a lot. So next thing we're going to look at is how to draw an angle. So like if I asked you guys to sketch a 90-degree angle, and I wasn't any more specific than that, is that a 90-degree angle?
Yes.
Sure. How about that?
Yeah.
Yeah, you can rotate it all different ways, but if we all sketch the angle in standard position, everybody's angle will look the same. Standard position has to do with where you place the initial and the terminal side. Well, actually, the initial. So, if you draw an angle in standard position, you have to do two things. If you have an XY axis, put the vertex right at the origin, and put the initial side on the positive x-axis. So there's an angle in standard position. Initial side is on the positive x-axis, vertex right on the origin. Okay, so let me take this angle in red and go like that. Is that still standard position?
No.
No, what's wrong with it?
It's not on the origin.
The vertex isn't at the origin. The initial side is okay. Initial side is on the positive x-axis. The vertex has to be at the origin. How about something like this.
No,
No. What's wrong with it now?
the initial side isn't on the x-axis.
Right. The vertex is at the origin, and the terminal side is on the y-axis, but the directions for standard position don't say anything about terminal side. It's the initial side that has to be in a certain spot. That's standard position. Okay, so what we're going to be doing in a little bit is I'm going to have you guys sketch angles in standard position. I'm not looking for you to get a protractor and sketch it perfect. I'm looking for like an approximation. So if something's 120, you should draw it a little bigger than 90. Okay, so you should, it's just a rough sketch. That's all. So if I go here, all of these, this angle is in standard position. I can't move the vertex from the origin, and I can't move the initial side. All I can do is move the terminal side. Okay. That angle that's in black, the two rays, is in standard position. Now, you notice as I drag it, there's some numbers down here that change. Does anyone know what that top one is?
The angle.
Measured in
degrees.
Okay, so that is one way to measure an angle, degrees. If I went back to that program I was just in and I made one full rotation, how many degrees would it say in one full rotation, Chris? 360. And specifically, if I did a counterclockwise rotation, that would be 360. Okay, going like this. Right back to where I started. 360. All right. How about if I did half a revolution? How much would that be? 180. Okay. And then how about a quarter revolution?
90.
That's 90. Okay. Now, there are two directions you can move when you move circularly, counterclockwise and clockwise. Which way you move is basically going to control whether or not you're talking about a positive angle, or what do you think would happen if you go clockwise? Yeah. Negative. Right? So you saw in that program, when I went counterclockwise, I generated a positive angle. And I can even go more than 360 if I want. Like that. Now that's 580. Counterclockwise is positive. Clockwise, let's go this way, is negative. Okay, so now here's the initial side, here's the terminal side, and it'd be nice if there was like a little arrow on the end of that red thing so you can see the direction. But I told you it was clockwise. And you can see that it's negative. Okay. Again, top number is in degrees. The bottom number is a different unit. Does anybody know the other unit besides degrees? Yep. Radians, yep. And we're going to talk how do you change radians to degrees and degrees to radians. That'll be the last thing we take a look at. All right. So you can definitely have an angle that's larger than 360. That's just more than one revolution. Now, I'm going to show you something, and I want you to look at it carefully and just answer, just what I'm asking. Okay. I'm going to take and put this right there at 90 degrees. Okay, what I want you to do is look at that and focus on where the red circle thing is on the perimeter of the circle. Okay, focus on where it is. That's all I want you to know. Now, I'm going to go like this. Comparing where the red circle was before to where it is now, how do those two positions compare?
Same position.
Same position. It's in exactly the same spot. So, if that little red circle thing is in exactly the same spot at 450, and it's in the same spot at 90, what does that tell you about a 90-degree angle and a 450-degree angle?
They're the same.
They're the same. For the purposes of doing anything with trig, 90 and 450 are the same thing, because that is in exactly the same spot. And the name for that is coterminal. Coterminal. Two angles that have the same initial and terminal sides. Okay? Look at it again. Initial goes right, terminal goes up. Put it at 450. Initial goes right, terminal goes up. Without that red spiral in there and without this number in the lower right, you wouldn't be able to tell the difference between 90 and 450. You can because of the red spiral thing. So I want to think about how you could convert 450 to 90 without actually using a diagram. You can do arithmetic involving adding or subtracting something. Yeah.
Subtracting 360.
Yeah. Okay. To find angles that are coterminal with each other, all you have to do is add or subtract 360. So the idea here is if I asked you to draw a picture of a 2500 degree angle, off the top of my head, I don't know what 2500 degrees looks like. That's a lot of extra rotations. Well, I can find an angle that's equivalent to 2500 by adding or subtracting 360 as many times as I need to. So, take 2500 minus 360, same thing, but it's still too big. Too big, too big, too big. Okay, 340, I can work with that. I know 360 is all the way around, so 340 is just a little bit short of going all the way around. Right. When you say 2500, that doesn't really mean anything to me because I can't think about that number, it's too big. Same thing if you gave me an angle of negative 2000. You've gone so many revolutions around in the clockwise direction. I'm not sure what that is. So I can add 360, and that's the same thing. Same thing. Same thing. Same thing. Same thing. 160. Okay, that I can visualize. 160, well, 180 is halfway, so 160 is a little bit less than half. It's easier for me to think about 160 than it is negative 2000. Great. So, we're going to look at an angle, we're going to sketch a picture of it, and then we're going to find an angle that's coterminal with it, that's positive, and coterminal with it, that's negative. So just adding and subtracting 360. Okay, so a 30-degree angle. How many degrees are basically in the first quadrant? 90. So 30 is how much of 90? A third. So what you want to do is draw your angle here so that it's about 1/3 of the way towards the vertical. Right? Just an estimate. Here's your initial, because it said standard position. And then just try to estimate about 1/3. That's good enough. All right, now I want an angle that's coterminal and positive and negative. So, what am I going to do to find an angle that's coterminal with 30 and positive?
Add 360.
Just add 360. What's 30 and 360?
390.
390. Now, what about an angle that's coterminal with 30 but negative?
Negative 330.
Negative 330. Yeah, just subtract 360. Okay. Any questions on that one? Okay, let's do this one. Okay, 145. Well, which quadrant is the terminal side going to be in? Yeah, it's going to be in quadrant 2. Now, can somebody be a little more specific? Is it going to be closer to the 90, closer to the 180, or right in the middle? Remember, this is 90, this is 180. So try to think about where 145 would be. Yeah.
Right in the middle.
If you average 180 and 90 to get what's right in the middle, it won't come out to 145. Yeah.
It would be more towards the 180.
It's a little more towards the 180. 135 is right in the middle. So you want to draw it. I don't know if that looks like it's a little bit more than in the middle. Close enough. So that's 145 degrees. Okay. What's an angle that's coterminal with 145 and positive? Well, how much?
105.
Not 405. What's 145 and 360? 505. Yep. So 505 and 145 minus 360 would give you negative 215. Okay. This one I'm not going to do coterminal. I just want to sketch it. What quadrant is the terminal side going to be in for negative 45? Jared?
4.
4. And where is it going to be? Closer to the 0, closer to the 270, or right in the middle?
In the middle.
It's exactly in the middle. Yep. Here's your initial. There's your terminal. You can put that if you want to show the direction. You don't have to. And that's how you'd sketch negative 45. To get a coterminal, add 360, subtract 360. That's it. All right. So now we're going to look at different ways we can classify angles depending on their size. Okay, we'll go through this, and then the last thing we're going to do is change between degrees and radians. What's an acute angle? Yeah? Okay, that's part of it. It has to be smaller than 90. But I could give you an angle that's smaller than 90. That's not acute. Anybody know what else it has to be? Yep.
Positive.
Yes, it has to be bigger than 0. So it has to be an angle between 0 and 90. Negative 10 is not acute. How about, what if the angle was exactly 90? What do we call that? Yep, a right angle. What do you call it if the angle is between 90 and 180? Bigger than 90, but smaller than 180.
Obtuse.
Yep, that's obtuse. Now, all of those classifications, acute, right, and obtuse, apply to a single angle. This next word applies to 2 angles. What are complementary angles? Complementary. Yep.
2 angles that add up to 180.
You're thinking of something else, which we're going to do next.
2 that are the same.
No, they don't have to be the same. Yep.
2 angles that add up to 180?
That's what Jared said the first time. It is 2 angles, yep.
360?
No.
That's supplementary.
We're going to talk about supplementary, which is what the first thing we said. Yep.
They add up to 90.
They add up to 90. And one more thing about them. I could give you two angles that add up to 90 that are not complementary. That's the same hint I gave you when we talked about acute angles. Yeah?
Bigger than 0.
Yes. They have to be bigger than 0, so they have to be positive. Or you could say two acute angles that add up to 90. Now the next type we already talked about, that was supplementary. And supplementary angles are two angles that add up to 180. Negative angles do not have complements or supplements. So if I ask you what the complement of 20 is, I'm asking you what do you add to 20 to get 90? That's the complement. Okay, but negative angles do not have complements or supplements. So,
You go back.
So let's practice just finding some complements and supplements. Okay, 48 degrees. What's the complement of 48 degrees? Chris?
42.
42. Yep. And the supplement of 48 degrees? Yep.
132.
132. Good. How about negative 18? What's the complement?
There isn't one.
There isn't one. What's the supplement?
There isn't.
There isn't one. No. No complements or supplements for negative angles. How about x? And I want you to assume x is acute. Because if x was bigger than 90, it wouldn't have a complement. So assume that it's acute. So how would you find the complement of x?
90 less than x, greater than 0.
Can you say it one more time? Like what would you type in on a calculator if you had to find the complement of x, pretending like x was a number? Yeah.
90 minus x.
90 minus x. And Brandon, how about the supplement? 180 minus x. Okay. So just some different terms we can use to describe either a single angle or a pair of two angles. Okay, the last thing we're going to look at is how we measure an angle. Degrees is one way, radians is another. Now, if you look at the word radian, does anybody see another word that it looks kind of like? Yeah.
Radius.
Radius. And a radius has to do with what shape?
Circle.
Circle. So, I'm going to show you visually what a picture of a radian would look like. It's not going to explain the mathematics of how you convert from radians to degrees yet. I'm just going to give you a visual, like a geometric description of a radian. So, let's say that you draw a circle. And in that circle, you put an angle with the vertex at the center. That's called the central angle. The rays of the angle are CA and CB. CA comes out from the center of the circle and hits the circumference right there. CB comes out from the center and hits the circumference right there. If you trace out from A to B, that path is called an arc. It's the arc intercepted by the two rays AC, CA and CB. Now, here's the part where I'm going to explain what a radian would look like. Let's say you take a ruler and you measure ray CB, and you get that distance. And then you take a piece of string and you put it on that arc. Okay, get it exactly on the arc, take it over to a ruler, straighten it out, and measure it. If the length of the radius is exactly the same as the length of that arc in red, then you've just drawn a picture of 1 radian. So if the length of your piece of string that you use to measure that arc comes out exactly the same as the radius of the circle, then you have a picture of 1 radian. Now, that statement is going to be very important for something that we do tomorrow. Okay, so remember that. If the length of the arc equals the length of the radius, then you have a picture of 1 radian. If the arc is smaller than the radius, then your angle is smaller than 1 radian. If your arc is bigger than the radius, then your angle is bigger than 1 radian. But if they're the same, then you have exactly 1 radian. That picture is not quite to scale. I think the arc there is a little bit bigger than the radius, if you were to measure it. So that's a little bit bigger than what a radian actually looks like. Probably be just a little smaller. Okay. So that describes a radian geometrically. Okay, so last thing I'm going to show you is how you change between degrees and radians. So, the way we're going to do it is I'm going to start out by drawing a picture of a circle. And the circle that I'm drawing is called a unit circle. All that that means is it's a circle with a radius of 1. 1 what? It doesn't matter. 1 foot, 1 inch, 1 unit, whatever you want to call it. It's a circle with a radius of 1. Now, I'm going to give you a fact. And this fact that I'm about to give you is going to help us to figure out how to change between degrees and radians. Because what we need right now is, in order to figure out how to convert between degrees and radians, you just need to know one fact that's true. For example, if I wanted to convert between feet and inches, can somebody tell me something that's true? Anything you want. Doesn't matter. It can be simple, complicated. Yep. 12 inches is a foot. What else could somebody have said besides that? There's something else that's true. What's that?
What's bigger than an inch?
What's that?
What's bigger than an inch?
Something numeric. Something else numeric that's true. Yep.
12 feet is 4 yards.
Inches to feet, though. Something else inches to feet, yeah?
Like 24 half inches in a foot.
24 inches in
24 halves.
half inches. How about we go with 24 inches in how many feet?
That's 2 feet.
2 feet.
2 feet, okay, that works. Half inches.
It's true, ain't it?
Yeah, I guess so. It is true. Any of those, both of these facts are true. So if you wanted to convert between feet and inches, and you told me one of these facts, then I could do something like this. Okay, they told me in 12 inches, there's 1 foot. So now you could say, well, how many feet in 70 inches? 70 inches, X feet. Just set up something like that and solve it. But the key is, you needed this to start. Now, the fact that this is a 12 and this is a 1, does that limit what numbers I could put over here? Like, could I only do 70 inches? No, I could do 72. I could do 87. The 12 and the 1, those are just a starting point. it doesn't limit the two numbers that you can put on this side. So that's what I need here. I need a starting point to figure out a connection between degrees and radians. And once you know one connection, like 12 inches equals a foot, you can figure out anything you want. You just need to know one connection. The connection we're going to figure out is how many radians to go all the way around the circle. Because we already know how many degrees to go all the way around a circle. 360. So if we can figure out how many radians go all the way around, then we're going to have a connection. 360 equals whatever. Okay, like 12 inches equals 1 foot. So in a unit circle, the measure, and I'm going to underline the important parts. In a unit circle, the measure of the angle in radians. The measure of the angle in radians is equal to the length of the arc. The measure of the angle in radians is equal to the length of the arc. So what that means is if you can tell me the length of the arc that goes all the way around the circle, that's exactly how many radians it takes to go all the way around the circle. Because the measure of the angle in radians is equal to the length of the arc. Now, if I want to go all the way around the circle, like this, we normally don't even call that an arc, because it's an arc that's so big it takes up the whole circle. What do we call an arc that goes all the way around the circle? The circumference. So, if you can tell me the circumference of this circle, that is equal to the angle in radians to go all the way around the circle. The length of the arc and the size of the angle are exactly the same. And I think most people are probably going to know the formula for the circumference of a circle. I hope. So, what's the formula for the circumference of a circle?
Something with pi.
Something with pi. Yep.
2 pi r squared?
Just 2 pi r. When you square things, then you're getting into area. So pi r squared is area. 2 pi r is the circumference. Now, I don't have just any random circle up there. I have a unit circle. What's the radius of a unit circle? 1. So the circumference of this circle is 2 pi times 1, which is how much? 2 pi. So, what you guys just found, you just told me the length of the arc all the way around the circle is 2 pi. What is the length of the arc equal to?
Radians.
The measure of the angle in radians. The length of the arc is 2 pi, and that number is equal to the angle measured in radians. So if this arc is 2 pi, what's the angle to go all the way around? 2 pi. So, let's just go to this. 2 pi, 1 revolution, to go all the way around is 2 pi, which is the same as 360. So you can write 2 pi equals 360, which is, how did I get this fact in the box? What did I do to each side? Divide by 2. Now, when you give someone a conversion between units, that's not normally how you do it. Okay, earlier, somebody said 1 foot equals 12 inches. What's the conversion between minutes and seconds?
60 seconds per minute.
60 seconds per 1 minute. Notice I just asked what the conversion was. He could have said there's 120 seconds per 2 minutes. That's true, but he didn't. He said per 1 foot. When you give someone a conversion, you usually give it to them with a 1. So let's get a 1 in this formula. Let's start by doing it on the left. What could I divide each side by to get a 1 on the left? Yep.
Pi.
Divide by pi. Divide by pi. Divide by pi. Now, pi divided by pi is 1 radian. So now you have 1 radian equals 180 divided by pi degrees. Now, what if you wanted a formula for 2 radians? You said, all right, I want to know 2 radians equals. What could you do to each side of this equation? Multiply it by 2 by 2. Now, if you do that out on the right-hand side, you'll have a number for 2 radians. What if you wanted to know 4 radians? What could you do? Multiply both sides by 4. What you're multiplying by isn't important. This is what's important. When you want to convert from a radian to a degree, you take whatever you want to convert, you multiply by 180, and you divide by pi. Whatever you want to convert. That's how you change radians to degrees. Multiply by 180, divide by pi. Now, to go the other way, you just reverse it. To go degrees to radians, do the opposite of what you did from radians to degrees. Instead of multiply by 180, you're going to divide by the 180. Instead of divide by pi, you're going to multiply by pi. Now, the steps to go from degrees to radians and radians to degrees are very similar. It can be confusing and easy to mix them up. The way to remember it, I'll show you. When I say degrees, I want you to think of the number. Let me go back here for 1 second. Think of the number 180. When I say degrees, think 180. When I say radians, think pi. If you can remember that thought, all of that is automatic. Degrees, 180, radians, pi. That's it. So I'll do maybe one example of each, and we can practice more tomorrow. I have like 4 or 5 of each. These are very, very quick. We'll just do one or two of each. Okay. So convert 30 degrees to radians. Your two options are pi over 180 or 180 over pi. This is how I remember it. Think of 30 degrees as a fraction. Where is degrees in the fraction? The top or the bottom? It's in the top. You're trying to cancel it out and get radians. So if you have degrees in the top, where would it have to go in your conversion to cancel out? It would have to go in the bottom. That means radians goes in the top. What number did I always say to think of when you think radians? Yeah. Pi. And what number do we always think of when we say degrees? 180. Pi, radians, 180 degrees. Now, degrees in the top, degrees in the bottom cancels out. And does 30 go into 180? How many times? 6. 30 goes in once, goes in 6, and that's how you leave your answer. pi over 6. And if I go back to this chart, put it on 30 degrees, if I can get it right on 30, it says pi over 6. Notice it doesn't say RAD. You got to get used to RAD being invisible. It's there, but it's invisible. You don't write it. Okay. Let's try this one. Where would degrees go to cancel out here? Bottom. What number do we always put with degrees?
180.
And that means what's in the top? Pi RAD is invisible. Degrees and degrees cancel. How many times does 45 go into 180? Yeah?
4 times.
4 times. 1, 4, and you get pi over 4. That's how you change a degree to a radian. Okay, I'll do one problem going radian to degree. Okay. The first time, I'm going to write RAD so you can see it. You've got radians in the top. Where would it have to go to cancel? Bottom. Degrees is in the top. What number do we always put with degrees? With radians? Pi is gone. Pi is gone. Radian and radian is gone. That's going to be invisible normally. 2 goes into itself once. How many times does 2 go into 180? 90. So you're left with 3 times 90 with the degree symbol. What's 3 times 90 degrees? 270. Yep. And that's pretty much how you change between degrees and radians. It's not too hard if you just remember where the 180 and the pi go. You can also round. We didn't do one where you round. I'll show you one where you round. You just use your calculator. So that's homework for tonight. It's mostly finding like the complement, supplement, finding an angle that's coterminal. They are all really, really, really fast problems. Okay, so all on page 323. Okay, we'll take a look at that tomorrow. We'll finish up our material for the week tomorrow. Remember, no test. Monday will be a review day. Last test we'll have before break will be 2 academic weeks.